Imagine you're building a modern web application that needs to store flexible, evolving data, like user profiles, chat messages, or sensor data. You decide to use MongoDB, a popular NoSQL database known for its document-oriented architecture. Unlike traditional relational databases that store data in tables with fixed schemas, MongoDB stores data in JSON-like documents, called BSON, that can have varying structures. This makes it incredibly adaptable to real-world data that often doesn't fit neatly into rows and columns. As your application grows, you realize managing the database infrastructure manually, setting up servers, backups, scaling, is time-consuming. That's where MongoDB Atlas comes in. Atlas is MongoDB's cloud-native, fully managed database service, available on major cloud platforms like AWS, Azure, and Google Cloud. With Atlas, you can deploy a production-ready MongoDB cluster in minutes. It takes care of high availability, automated backups, monitoring, and even security best practices like encryption at rest and role-based access control. To interact with the data visually and explore your collections without writing long queries in the terminal, you use MongoDB Compass. Compass is the GUI, graphical user interface, for MongoDB. It provides a user-friendly way to browse your databases, run ad hoc queries, view schema analytics, and even analyze query performance. With Compass, you can visually inspect data and indexes, which helps a lot during development and debugging. So, in your tech stack, MongoDB is your powerful, flexible document database. Atlas is your cloud platform that manages and scales MongoDB effortlessly. Compass is your window into the database, offering a visual interface for developers and data engineers alike. After setting up your MongoDB database, perhaps on your local machine or via MongoDB Atlas, you often find yourself needing direct, hands-on control over your data. That's when you turn to the MongoDB shell, a command line tool that lets you talk directly to your database using simple, JavaScript-like commands. You launch the shell, connect to your cluster, and now you're inside the heart of your database. You decide to manage a collection called users, where you'll store and manipulate user information, creating new users. To add your first user, you simply type db.users.insert1. Name: Alice. Email: alice@example.com. Age: 28. Is active: true. Semicolon. Just like that, a new document is saved into your database. You continue by adding a couple more users at once. db.users.insert many. Name: Bob. Email: bob@example.com. Age: 35. Name: Carol. Email: carol@example.com. Age: 24. Now your users' collection is beginning to take shape. Reading the data. Curious to see what's in the collection, you run db.users.find. A list of all user documents appears. You can be more specific, of course. Maybe you want to find users over 30. db.users.find age, $GT, 30. You even pretty print the results to make them easier to read. db.users.find, pretty. Updating user info. Next, you realize Alice's information needs an update. She just turned 29 and is no longer active. So you type db.users.update1. Name: Alice. $set. Age: 29, is active, false semicolon. You can also update multiple users at once. Suppose you want to tag all inactive users with a new status. db.users.update many. Is active, false. $set. Status: inactive semicolon. And when Bob celebrates a birthday, you increment his age. db.users.update1. Name: Bob. $incorporated. Age: 1 semicolon. Deleting users. Finally, some users need to be removed. Carol no longer uses the service, so you remove her. db.users.delete1. Name: Carol. Or maybe it's time for a cleanup, removing all users marked as inactive. db.users.delete many is active, false. Great. Here's a narrative-style explanation of MongoDB aggregation, written in a way that's clear, engaging, and well-suited for an audiobook format. Chapter: Understanding MongoDB Aggregation, Turning Raw Data into Insight. Imagine you're managing a MongoDB database for a podcast platform. You have thousands of documents in a collection called episodes. Each document represents a podcast episode, with fields like title, host, duration, category, and listeners. One day, your product team asks, how many minutes of content have we published this month? Which hosts are most popular? What's the average length of episodes in the technology category? Now, this is where aggregation becomes your best friend. Aggregation in MongoDB is like building a pipeline for your data. Instead of simply pulling documents as they are, you pass them through stages that can filter, group, reshape, and summarize them, kind of like a series of conveyor belts in a factory, transforming raw data into neatly packed insight. Let's walk through an example. Stage 1. Match, filtering the right data. First, you need to narrow down your data. Say you want to focus only on technology episodes. $match. Category, technology. This stage works just like a find filter. It selects documents that meet your criteria. Stage 2. Group, summarizing data. Now that you have only technology episodes, you want to find the average duration. You use the $group stage. $group. _ID, null. Average duration. $average, $duration. Here, _id, null means you're grouping all the documents into a single group, and you're calculating the average of the duration field. Want to see how many total episodes each host has? You'd group by hostname. $group. _ID, $host. Total episodes. $sum, 1. Stage 3. Sort, ranking your results. Next, maybe you want to find out who your most prolific hosts are. After grouping, you add a $sort stage. $sort. Total episodes, -1. This orders the hosts by the number of episodes they've published, from most to least. Stage 4. Project, shaping the output. Sometimes, you want to clean up the output or rename fields. The $project stage helps with that. Suppose you want to show only the host name and their episode count. $project. Host, $_ID. Total episodes, 1. _id, 0. Now your results are neat and ready for a dashboard, or a product meeting. Putting it all together, the pipeline. When you combine these stages, it looks something like this. db.episodes.aggregate. $match. Category, technology. $group, _ID, $host, total episodes, $sum, 1. $sort, total episodes, -1. $project, host, $_ID, total episodes, 1, _ID, 0 semicolon. In just a few lines, you've gone from thousands of raw episode documents to a clear summary of your top-performing tech hosts. Aggregation pipelines are powerful because they help you ask deep questions of your data, without ever needing to export it. You can filter, transform, and analyze in real time, directly in MongoDB. So whether you're building reports, computing metrics, or feeding a dashboard, the aggregation framework turns MongoDB into not just a data store, but a powerful analytics engine. Chapter: Speeding Things Up. MongoDB Indexing Explained. Picture this: you're running an app that streams audiobooks. Your MongoDB database has grown to hundreds of thousands of documents in a collection called books, and users are constantly searching for titles, filtering by author, or browsing by genre. At first, everything worked fine. But now, queries are starting to slow down. Users complain that searches take too long. That's your cue to reach for a powerful tool: indexing. Let's break it down. What is an index? In simple terms, an index in MongoDB is like the index at the back of a book. Instead of flipping through every single page to find a word, you jump straight to the right spot. MongoDB indexes work the same way. They speed up the process of finding documents based on specific fields. Without an index, MongoDB has to scan every document in the collection to answer a query. This is called a collection scan, and it's fine when you have a few documents. But with thousands or millions, it becomes slow and expensive. Creating a simple index. Let's say users are often searching for books by title. You can help MongoDB speed this up by creating an index on the title field. db.books.createIndexTitle. 1. The 1 means the index is sorted in ascending order. If you wanted descending order, you'd use -1. Once this index is in place, MongoDB can jump straight to the documents where the title matches, instead of checking every single one. Compound indexes, searching on multiple fields. Now suppose users often filter by both author and genre. You can create a compound index that covers both. db.books.createIndexAuthor. 1. Genre. 1. This helps MongoDB quickly find documents that match both criteria, say, all science fiction books written by Isaac Asimov. One thing to remember: the order matters. An index on author 1, genre 1 helps with searches on both fields or just on author, but not if you're searching only by genre. Unique indexes, enforcing rules. What if each book should have a unique ISBN? You can enforce that with a unique index. db.books.createIndex is bin. 1. Unique. True. This not only speeds up searches by ISBN but also prevents duplicates from being inserted. Text indexes. Full text search. For audiobooks, users might want to search by keywords in a description. You can use a text index for that. db.books.createIndex description. Text. Now users can search with db.books.find$text, $search, space travel. MongoDB will return all documents where the description includes those keywords. Viewing indexes. To see what indexes exist on a collection, db.books.getIndexes. And to remove one, db.books.dropIndexTitle_1. Indexing is a superpower. Use it wisely. Indexes are amazing for read performance, but they come with trade-offs. Every time you insert or update a document, MongoDB must also update the index. So if you over-index, write operations can slow down. That's why it's important to index the fields you query often, but not everything. Use MongoDB's explain plans to see which queries benefit most from indexing. In summary, indexing is how you keep your MongoDB queries fast and efficient, even as your data grows. Just like a library catalog helps readers find books in seconds, a well-designed index turns your growing audiobook app into a high-speed, responsive experience for every user. Chapter: Growing Without Slowing, Sharding and Horizontal Scaling in MongoDB. Imagine your audiobook platform has become wildly popular. Thousands of users are listening at any given moment. Your MongoDB database now stores millions of documents, books, authors, listener stats, playback history, and more. Queries are getting heavier, the load is increasing, and a single server just isn't cutting it anymore. You're facing a classic challenge. How do you scale MongoDB so it can grow without slowing down? That's where sharding enters the story. What is sharding? Sharding is MongoDB's strategy for horizontal scaling. Instead of storing everything on one server, MongoDB splits your data across multiple machines, called shards. Each shard holds a portion of your collection, and MongoDB knows where to find everything. Think of it like this. You're organizing a massive library. Instead of putting all books in one room, you split them by genre. Fiction in one room, nonfiction in another, science in a third. Each room, or shard, handles a smaller, more manageable piece of the whole. The components of sharding. In a sharded cluster, MongoDB relies on three key components. 1. Shards. These are the actual data-bearing servers. Each shard stores a chunk of your data. 2. Config servers. These hold metadata about where each piece of data lives. They're the brain of the operation. 3. Mongo's router. This is the entry point for your app. It takes incoming queries and routes them to the correct shards based on the data. To your application, it still looks like one big database. Behind the scenes, the Mongo's router makes everything seamless. Choosing a shard key. Sharding doesn't work on its own. You need to tell MongoDB how to split the data. This is where the shard key comes in. It's a field, or fields, you choose to determine how documents are distributed. Let's say you're sharding your listens collection, which logs every time a user plays a book. You might shard by user ID, which keeps all of a user's activity on the same shard. sh.shardCollectionAudio.listens, user ID 1. Choosing the right shard key is critical. If you pick one with poor variety, say, a value that doesn't change much, all your data might go to just one shard. That causes hotspots and defeats the purpose of sharding. A good shard key is high cardinality, lots of unique values, evenly distributed, and frequently used in queries. How sharding helps. Once sharded, your database can handle more reads and writes in parallel. Scale out by simply adding more shards. Store more data than a single machine could hold. For your audiobook app, this means you can keep growing, more users, more playback data, more books, without slowing down. What about replication? Sharding isn't a replacement for replication. They often work together. Each shard in MongoDB is usually a replica set, which means it has copies of data for high availability and failover. So in a full-scale deployment, MongoDB isn't just sharded, it's sharded and replicated. This combination gives you the best of both worlds. Sharding for scalability. Replication for reliability. Final thoughts. Sharding is MongoDB's answer to big data. It helps you break through the limits of single-server performance and move confidently into large-scale territory. With smart shard key design and a well-balanced cluster, you can make sure your audiobook platform is ready for anything, from a quiet midnight listener to a global surge of users tuning in to the next bestseller. Chapter: Always Online, MongoDB Replica Sets and High Availability. Imagine this. It's late at night, and a user in Tokyo hits play on an audiobook. Meanwhile, another user in New York is uploading a new podcast episode. Your MongoDB database is handling traffic from all around the world, 24/7. Now imagine your primary MongoDB server crashes. What happens to those users? If you've set up your database correctly, with replica sets, the answer is simple. Nothing happens. The system keeps running. The Tokyo listener keeps listening. The New York podcaster keeps uploading. That's the magic of high availability. And in MongoDB, it's powered by replica sets. What is a replica set? A replica set is a group of MongoDB servers that all hold the same data. At any given time, one of them acts as the primary, while the others are secondaries. The primary handles all writes and most reads. If the primary goes down, one of the secondaries is automatically promoted to be the new primary. This process is called failover, and it happens in seconds, with no human intervention. Let's say your replica set has 3 members. 1 primary. 2 secondaries. If the primary suddenly fails, due to hardware issues, a network glitch, or even a planned maintenance task, MongoDB detects the failure, holds an election, and promotes a secondary to take over. Your application might see a tiny blip, but it won't go offline. How replica sets keep data in sync. Here's how it works under the hood. When you write to the primary, say, saving a new audiobook, MongoDB logs the operation and replicates it to the secondaries. This replication happens almost in real time. Secondaries continually catch up by reading the op log, or operations log, from the primary. So if your primary ever fails, the secondaries are already up to date and ready to jump in. Read scaling with replica sets. In some cases, you can also use secondaries to help with read scaling. For example, you can route analytics or reporting queries to a secondary node to reduce the load on the primary. db.getMongo. Set read pref secondary. However, keep in mind that secondaries might be slightly behind the primary, so for critical real-time reads, it's safer to stick with the primary. Write concern and read concern. MongoDB gives you fine-grained control over data consistency with settings called write concern and read concern. Write concern lets you specify how many nodes must confirm a write before it's considered successful. For example, majority ensures that most nodes have saved the data before proceeding. Read concern lets you control how fresh the read data must be. If you're okay reading slightly older data, you can read from secondaries. If you need guaranteed up-to-date results, you read from the primary with majority read concern. Replica sets in a global app. For a global audiobook app, you might distribute your replica set across multiple data centers. You keep a primary node in Europe, a secondary in North America, and another in Asia. That way, your app stays resilient, even if an entire region goes offline. You can even configure hidden secondaries for backups or analytics-only workloads. They won't be promoted to primary or handle regular reads, but they'll quietly mirror all data behind the scenes. Final thoughts. Replica sets are MongoDB's secret weapon for resilience, reliability, and peace of mind. They make sure your app is always available, even during failures, and your data is safely stored in multiple places. In a world where users expect uptime all the time, replica sets help you meet that expectation. No matter what happens to your servers, your stories keep streaming, your uploads keep flowing, and your app keeps running, just the way it should. Next audiobook chapter to focus on MongoDB transactions and data integrity. Great question. Here's how you create a replica set in MongoDB, explained clearly and concisely, ideal for audiobook narration or step-by-step use. Chapter: Building a replica set. Step-by-step guide to high availability. Now that you understand why replica sets are powerful, let's walk through how to actually create one in MongoDB. We'll start with a simple 3-node replica set, all on the same machine for testing, or across servers in production. Step 1. Install MongoDB on all nodes. First, make sure MongoDB is installed on each machine, or each port if you're using one system. You'll need at least 3 MongoDB instances, 1 primary and 2 secondaries. Step 2. Create data directories. Create separate folders for each MongoDB instance's data. For example, mkrp/data/rs0/data/rs1/data/rs2. Step 3. Start each instance with replica set config. Now start 3 MongoDB processes on different ports, each pointing to its own data directory and using the same replica set name, for example, rs0. MongoDB port 27017 dpath/data/rs0 repl set rs0 fork log path/data/rs0/mongod.log. MongoDB port 27018 dpath/data/rs1 repl set rs0 fork log path/data/rs1/mongod.log. MongoDB port 27019 dpath/data/rs2 repl set rs0 fork log path/data/rs2/mongo.log. Step 4. Connect to one node with the Mongo shell. Open the Mongo shell on one of the instances. MongoDB port 27017. Step 5. Initialize the replica set. Now use the following command to initialize the replica set. rs.initiate _id rs0 members _id 0 host localhost :27017 _id 1 host localhost :27018 _ed 2 host localhost :27019 . MongoDB will configure the replica set, elect a primary, and start syncing data between members. You can check the status with rs.status. If all goes well, you'll see one primary and two secondaries listed. Optional, add more nodes later. If you want to add another node later, rs.add localhost :27020. And to remove one, rs.remove localhost :27018. And that's it. You now have a running MongoDB replica set. Every write you make to the primary will be automatically replicated to the secondaries. Perfect. Here's the next audiobook-style chapter on MongoDB transactions, focusing on how they help you maintain data integrity across multiple documents and collections. Chapter: Keeping it all together, MongoDB transactions and data integrity. In the real world, some operations just need to be all or nothing. Imagine you're building a payment system for your audiobook platform. A user buys a premium subscription. At that moment, two things need to happen. 1. The user's account is updated to Premium.2. A transaction log is recorded in a billing collection. Now here's the problem. What if one update succeeds and the other fails? You can't have users upgraded without a record of payment. And you definitely don't want to log a payment that never went through. This is where MongoDB transactions come in. They ensure that multiple operations across documents and collections either all succeed together or all fail together, just like transactions in traditional SQL databases. What is a transaction? A transaction is a sequence of operations that runs in a single atomic unit. If everything in the transaction succeeds, the changes are committed. If anything goes wrong, MongoDB rolls back the entire operation, like it never happened. This is crucial for maintaining data consistency, especially in financial systems, inventory tracking, or user permissions. Starting a transaction, using the shell. Let's walk through how to perform a transaction in the MongoDB shell, MongoDB. First, you need to be connected to a replica set or sharded cluster. Transactions only work in those environments. Now, let's begin. Const session equals db.getMongo. Start session. Const users equals session.get database audio. Users. Const billing equals session.get database audio. Billing DAO session.start transaction. Try users update 1. Username, John_Doe. $set. Subscription, premium Billing insert 1. Username, John_Doe. Amount, 9.99. Currency, USD. Timestamp, new date Session.commit transaction. Print transaction committed. Catch, error. Session.abort transaction. Print transaction aborted due to error, plus error. Finally, session.end session. Let's break it down. You start a session. You start a transaction within that session. You perform multiple operations. Here, one update and one insert. You commit the transaction if everything works. If anything fails, you abort it and nothing is saved. This ensures your data stays reliable and consistent. Close lock with key emoji. Transactions also work with read and write concerns. You can configure things like write concern and read concern to control how strongly MongoDB guarantees that data has been saved or read from a majority of nodes. For example, session.start transaction. Read concern. Level, snapshot. Write concern. W, majority, semicolon. This helps ensure multi-document consistency across distributed systems. Real-world examples of when to use transactions. Booking a seat in an audiobook live Q&A event and deducting from user credits, creating a user profile and initializing their settings at the same time, moving a user's listening data to another account after a merge request. In all these cases, you're updating more than one document, and failure in any part should cancel the entire operation. Final thoughts. MongoDB started as a fast, flexible NoSQL database for documents, but now, with transactions, It's grown up into a system that can handle complex, enterprise-grade use cases. If you're working with related operations that must stick together, transactions are your safety net. They ensure your app's behavior matches the real world. Either everything happens, or nothing happens at all. MongoDB does not implement a traditional two-phase commit protocol internally, like some relational databases or distributed systems do. However, it provides a way to implement two-phase commit manually using its features, especially since version 4.0, which introduced multi-document transactions on replica sets, and later on sharded clusters in version 4.2.